Okay, let's begin. So thank you for being here. I'm very happy to have Marcel Binz here. And you accepted the invitation to come to talk about your work. Marcel got his PhD in Marburg and then worked a lot between first Tübingen and now Munich, but still with a lot of association connection with Tübingen. And I mean, my interest, the interest of the lab, and I hope of the department about Marcel's work is that he kind of pioneered an investigation of the connection between large language model and cognitive psychology, both in terms of how we can exploit paradigm from our field, looking as a psychologist, from our field and to better understand large language models, but also how we can use large language models to better understand human beings. And I guess that most of his presentation will be about this latter part and his work going on now. His work are published in big journals like Perceived National Academy of Science, Ecological Review, Behavior and Brain Science, works that especially looking at students, you should read. Okay? And yeah, and that's all. So thank you for being here. Welcome.
So, thanks for the kind introduction and also thanks for inviting me. So I will try to speak without a microphone in the room. Can people in the back hear me well? Yeah. Okay, perfect. And also in terms of questions, so we have a bigger question session at the end. But if you have clarification questions, feel free to just raise your hand, interrupt me. I'm happy to take smaller questions in between. So I will talk about foundation models of human cognition today, which are models that do not try to explain human behavior in one specific domain, but instead offer a unified take on the human mind, can predict, explain human behavior across several different domains. So to kind of motivate this a bit, I want to start by giving an example. So as many of you probably already know, back in 2016, Google DeepMind has really shocked the world with the release of a system that was called AlphaGo, which was able to play the board game of Go at a superhuman level. And back then, that was really considered a milestone of AI and machine learning research, especially considering that many experts predicted that it would take a lot of more years until we have a system, a computer system, that can play or can beat the best players at the game of Go. Now, while that was an amazing engineering achievement, AlphaGo was really only able to play the game of Go and not do many other things besides that. And that was really exemplified by the fact that there was a human engineer sitting at the board executing the moves that were suggested by the machine. Now, if we compare this to people, we know that people do not only play board games, they do many other things. And we have accomplished quite a lot of amazing stuff over the years. For example, we build rockets that send people to the moon. We invent vaccines that save millions of lives. We are creative, we create inspiring art, and we communicate with other people. We somehow take all the knowledge that we have and teach it to the next generation. And really how people manage to accomplish all of these things is the question that keeps me up at night. I think it's fair to say pretty much you can take any meaningful behavior back. Now, how does all of that happen? I think in order to get at this question, we need to take a domain general approach to human cognition and study it from different angles. Angles such as decision-making, deliberation, exploration, causal reasoning, and many others. And I think right now in cognitive science, the state of the field is that we have a reasonable, solid understanding of how human behavior and how human cognition work in some of these subdomains, but we pretty much have no clue how all these things interact with each other and how they are connected. And on the other hand, it's really important to study all of these things to understand the human mind in the broadest sense. Now, that is not a new thought that has been recognized by researchers for many years already. For example, Newell already said in 1992 that we need to come up with unified theories of cognition because these theories are the only way of how we can bring this wonderful and increasing fund of knowledge that we have somehow under intellectual control. And back then, his approach was based on the idea of cognitive architectures, which involved many hand-designed components, and then he wanted to specify how all these different sub-processes interact with each other. Now, we have almost 35 years after he made the statement, and we still don't have any or we are not even anywhere close to a unified model of human cognition. And I think this approach of designing cognitive architectures for this purpose is kind of failed. It's fair to say that it a bit failed its promise. And that is because it's just so complicated to do. You have to think about so many things, hand design all of these, and it just gets way too complicated. The alternative is to take a data-driven approach to this problem, to figuring out how these unified models of human cognition could look like, and discover them based on using data. And this essentially is what this talk will be about. I present how we can discover these unified models of human cognition in a data-driven way, and I present the first prototype of a model that goes, at least to some extent, in this direction. So question is, so this needs a bit of setup before I can actually get there. So the question is, how do we come to this point? So recently, as many of you probably know, if you don't live under the rock, we have seen the emergence of a class of computational systems that could, at least to some extent, be considered as domain general. Of course, I'm talking about large language models. So these are large neural networks trained on huge amount of data taken from the internet to predict the next word for a given text sequence. But as we scaled up these models in the recent years, we found that they have many emergent abilities. And modern large language models can, amongst other things, solve challenging reasoning problems. They can translate from one language to another, and they can write computer code. Now, the fact that these are to some extent could be considered as domain general agents obviously caught my attention. And about almost 2 years ago, or a bit more than 2 years ago by now, started to wonder whether it's possible to take some of these models and place them into psychology lab, run psychological experiments on them. Now, if that would be possible, that would be quite a powerful approach to understand how these black box machines learn, how they think, and how they make decisions. And who knows, by studying these models using tools from cognitive psychology that psychologists have developed over the last years, maybe we would even find out that we, through a happy accident, have built these unified models of human cognition already, if they would truly behave in human-like ways in these kind of experiments. We summarized our results in a paper that is called Using Cognitive Psychology to Understand GPT-3. It's been now published in PNAS. And in this paper, we have taken the back then most powerful language model out there, GPT-3, and subjected it to a battery of canonical experiments from the cognitive psychology literature. So these cover domains like decision-making, deliberation, exploration, and causal reasoning. I don't have the time today to go over all of the results that we have in the paper. So instead, what I decided to do is I pick one of these domains as an example, illustrate how this general approach to understanding large language models using tools from cognitive psychology can work. And then if you're interested in more details about some of the other domains, I encourage you to check out the paper. And the particular setting that we look at is the question of how do people solve the trade-off between exploiting what they already know and exploring the world around them. Now, in the lab, this is often studied in a very simplified setting. It's known as a multi-armed bandit setting. In this case here, we have a two-armed bandit problem where the decision maker repeatedly has to choose between two different options. You have a red option and a green option. In each trial, decision maker has to pick one of these options and observes a reward based on whatever option is chosen. And this process then repeats for multiple rounds, and typically the task of a participant in this experiment is to accumulate as many rewards as possible over the entire experiment. In the paper, we used a particular version of the task that is also known as the horizon task, where participants are first presented with 4 observational trials, so going from the top to the bottom, where they are instructed to choose a particular option, and then they get reward feedback for that option. And after these 4 forced choice trials, there are a number of free choice trials where participants can freely decide what action to pick. Now, in order to test this experiment on large language models, we developed a text-based version of this task, which is typically presented in this visual format. And this looks roughly as follows. So first, we give these models a general description of the task, describing what is the task even about. So in this case, we say that you are going to a casino that owns 2 slot machines, and you can earn money each time you play on these machines. And then we give a history of previously observed examples. So we say machine F in the past has delivered $45, machine J has delivered $35, and so on. Let me tell the model your goal is to maximize the sum of received dollars in this experiment within a certain number of additional rounds of play. So this one round here it says 1 additional round, which would be the case for this, but there might be more additional rounds where decision maker has to interact with this task. And then we ask, which machine do you choose? And the large language model would solve these kind of problems by simply completing this prompt that is shown here, either responding machine F or machine J. And once the model does a response, we simulate this response, generate the corresponding reward, and append that observation to this history of observations. So we took this experiment, simulated GPT-3 on it, and first looked at how does the model even perform the task. And when we do that, it's shown in this plot here, and compared also to human performance. Here, in this case, performance is measured in terms of regret, which are the amount of rewards that the agent failed to get. So lower means better performance. In the dotted red line on the top, you see the performance of a random agent that would randomly pick one of the 2 choice options. And we see GPT-3 is actually quite good at this task, much better than chance level, and almost indistinguishable from human performance. So now that, of course, led us to the question, do these models apply similar strategies to solve these problems as people, or do they solve these tasks in completely different ways? So and we investigated this by looking at their choice behavior. For this, we look at the choice behavior in the first free choice trial, so the trial after you have observed these 4 observational trials. Choice behavior is plotted on the right here, where on the x-axis you have the mean difference between the rewards, between the 2 options, difference between the more informative and the less informative option, where the more informative option is the one that has been observed fewer times in the observational trials. So in this case, it would be the green option. And this is plotted against the probability of selecting the more informative option. And what we see in this plot is if the more informative option is much better in terms of rewards than the less informative option, we are on the right side. And in these cases, people tend to pick the more informative option more frequently. On the other hand, if the less informative option is better, we are on the left side, and then people avoid the more informative option, pick the less informative option. They are not perfect at this task, as indicated by the sigmoidal choice curves, but overall, people do a pretty good job here. And in this condition, it's also important to mention when there's only one free choice trial, the optimal strategy would actually be to simply exploit all the knowledge that you have. And you can do this by computing expected values for both of these options and then simply picking the option with the highest expected value. So now let's compare that choice behavior to GPT-3. And when we do that, we find that GPT-3 has a very strong bias towards avoiding the more informative option. It really likes to pick the less informative option, which in this case would be the red one. And this is a really strong form of stickiness behavior. Just likes to repeat what it has previously seen in its context. So here, this is one example where we already see, although performance on average in this experiment was the same, choice behavior of GPT-3 is actually quite different from the choice behavior of people. You can look at the second case. So now we are considering a case where you have to make multiple choices. So you're not only restricted to one, but you have 6 additional choices that you can make. And we again consider the choice behavior in the first free choice trial. In this case, exploitation is not the optimal strategy anymore, but you instead have to manage this trade-off between exploration and exploitation. Sometimes it might be good to explore in the beginning a bit, because in the long run, over these 6 choices, what you learn when you explore might be beneficial to get more rewards in the long run. And one type of exploration strategy that people are known to apply is called directed exploration. So this is a type of exploration strategy where you sample options for which you can learn more about an environment, for which you can acquire more information. And in this case here, this would correspond to the options that have been observed fewer times in the free choice trials. So in this case, the green option. And we see when people have to make 6 choices as opposed to 1, 6 choices is now the dotted line in this plot, where 1 choice is a solid line. We see that people tend to pick the more informative option and thereby explore their environment whenever it's beneficial to do so. So they're really able to modulate their choice behavior depending on the number of additional choices that you have to make. Now, comparing this to GPT-3 again, we see that GPT-3 is not able to modulate its choice behavior based on the number of remaining choices that it has to make, just does the same thing no matter if you give it 1 additional choice or 6 additional choices. So really, it's not able to apply this type of directed exploration behavior in a strategically meaningful manner. So here, in this, what I wanted to show basically is that GPT-3, although it performs quite well in this task, is even indistinguishable from human performance, it solves these tasks in very different ways when you compare it to human subjects doing the same problems. Now, in the paper, we did a bunch of other studies. We looked at decision-making, for which we looked at a risky choice paradigm, where people have to sample between 2 options that are given via description. We looked at a case of deliberation, for which we used a 2-step task, which is a paradigm to disentangle model-based from model-free reinforcement learning. We looked at the horizon task that I just talked about, and we looked at causal reasoning. And across all of these tasks, performance of GPT-3 was actually surprisingly good. And maybe that is, and even outperforming human subjects in some of these tasks. And maybe by now that is much more accepted that this is the case, but back then when we first ran these studies, this came as a huge surprise to me, that you could just take any experiment from the psychology literature, translate into text, give it to these models and get meaningful responses back. I actually still remember going to the lab 2 years ago or 2.5 years ago saying, I'm running these experiments, bandit studies on GPT-3, and it seems to be better than chance level. That's crazy. But I think by now there have been a lot of follow-up works and it's much more accepted. One common exception was causal reasoning paradigm, and I come back to that in a second. So now when we looked, however, how these models solve these tasks, we found that they often do so in very unhuman-like ways. In the case of decision-making, we found that these models have some of the cognitive biases that you also find in people, but there are also a lot of cognitive biases that you find in people that are not present in these models, and probably the other way around, although we didn't look at that specifically. In the case of deliberation, we perhaps somewhat surprisingly found that these models engage a lot in model-based learning and model-based reasoning, which is a type of learning that people are known to use as well, but people typically mix it with a combination of model-free learning as well, which we did not find in these models. And then in the case of exploration and causal reasoning, we found the biggest differences when comparing people to GPT-3. And I think that to some extent makes sense as well if we remind ourselves of how these models are trained. They're simply trained to passively predict the next word for a given text sequence. And when we look at these tasks, we notice that these are 2 tasks that actually require active interactions with the world around us to solve them in a meaningful way. And I think this mismatch between what is required by the task and how these models are trained could also explain the biggest mismatch in terms of how human-like these models are on these particular problems. We did a bunch of follow-up projects on this first paper. I sadly don't have the time to talk about them into too much detail, or most of them, but I want to briefly summarize and point you towards these projects. On one project, the first one here, we presented a language model with an anxiety-inducing prompt. So we essentially asked us, tell me in 100 words about a situation that made you anxious. And then we gave this model this prompt and tested it on several downstream tasks and look how well does this additional anxious, anxiety-inducing prompt change their behavior. And we found indeed that when you give these models anxiety-inducing prompts, that changes their behavior a lot, and most importantly, increases how biased this model is against certain groups of people. Particularly, they become much more ageist, much more racist, much more sexist, and so on. And that is quite important to know when we think about applying these models in the real world, for example, in the context of psychiatry. In the second example, we found that large language models have a very strong tendency for an optimism bias, which is also a bias that is known in people and which says that people and also these large language models learn much more from positive prediction errors than from negative prediction errors. And again, this is showing really how we can use tools from cognitive psychology to understand how these models internally work. And that is very important to figure out or very important to know when we want to use these models in certain applications. Certainly, if you want to teach these models a new skill, you want to know, is it actually able to learn the skill or not? And then, lastly, we had a recent project where we extended the ideas from the PNAS paper that I just presented and created a cognitive benchmark for large language models, where we tested a large set of models on different experiments from cognitive psychology and really tried to create a phenotype along multiple dimensions on what kind of skills these models are good at and what kind of skills these models are not good at. This looks very similar, what we did there, to what I've just presented. Essentially, we have taken several different experiments, classical experiments from the literature. So here's a probabilistic reasoning task, here's a balloon analog risk task, and so on. And we created text-based versions on them. We then simulated the models on these kind of tasks and extracted 10 different behavioral metrics, like how model-based these models are, how strong are they in terms of metacognition, how risk-taking they are, and many other things. And then we can also compare these different metrics as reference point against how humans score along these different dimensions. So I won't go into too much details. The only thing I really want to show is that in the original PNAS paper, we looked at, by now, a rather old model at GPT-3. And in this benchmark, we have a lot of new models as well, GPT-4, Claude 2, a bunch of Google models, and so on. And what you see here in this plot is the cognitive phenotype of these models along all dimensions, where the dotted lines in these plots, the 0 line corresponds to the metric of a random agent in this task, and the second dotted line at 1 corresponds to the value that the average human population has. And kind of what we see here, even though we scale these out models more and more, they still don't become more human-like, at least when you consider these multidimensional measure of their behavior. Now, this is not the only work that has found this out. There's, for example, another recent paper where the authors have shown that in the newer GPT models, you find this emergence of economic rationality. So these newer models are, in fact, much more rational than the older models, and they lose a lot of the cognitive biases that you find in people. Similarly is this paper here, where essentially the title says it all. It says human-like intuitive behavior and reasoning biases have emerged in large language models, at least to some extent, but they largely disappeared in these newer models like ChatGPT again. So really that seems to indicate when we want to think about how can we get these unified models of human cognition, simply scaling up a large language model, make them more complex, train them on more data, is perhaps not the right direction to go to. So what can we do instead? How can we make these models more human-like to get towards these unified models of human cognition? One approach that we have recently proposed is that we can take a pre-trained large language model that is trained on a large-scale text corpus from the internet, a bunch of popular models out there. One popular model class is this class of models called Llama, which was released by Facebook, or Meta AI, that we used in this project as well. And then we want to fine-tune these models on domain-specific data to make them more human-like. And one obvious source of data is, again, data from psychology experiments. Psychologists over the last decades or even centuries have collected so much data, so we have really an abundance of data that we can use for this. And now we want to see, okay, what happens when we fine-tune these models on data from psychological experiments? We did this, and we did this in a paper that's called Turning Large Language Models into Cognitive Models, where we fine-tuned this Llama model on a data set of psychological experiments, and that led to a model that we called Centaur, in analogy to this musical creature that is half human and half a horse, really looking long for something that is half llama and half human, but we couldn't find anything. So then we had to somehow settle for this nearest neighbor, and that led to Centaur. And then we take this model and evaluate it on a bunch of holdout experiments. I won't talk so much about this project here, or this particular paper, because I think this is like a proof of concept. Instead, what I want to do is I want to talk about an ongoing project where we essentially take the same idea and massively try to scale it up. And in order to do this, we have created this huge data set, which is a collection of psychological experiments that are all transcribed into a text-based form, so that we can use this data set to fine-tune a large language model. This is really a huge-scale collaborative effort, involves over 40 collaborators. We have by now transcribed nearly 200 experiments into this format. This reaches really an unprecedented scale, contains 14 million human choices. And if you translate it to text tokens, you find that it's around 1 billion tokens. And this data set really includes most of the classics of cognitive psychology. You find some similarity judgment tasks, risky choice, decision from experience, balloon analog risk tasks, and many others. The space mostly right now covers experiments from learning and decision-making literature, because that is what I'm most familiar with. But I hope to extend this at some point in the future to much more general settings as well. We have a bunch of bandit problems, simple bandit problems, but also more complex ones, contextual, drifting bandits, and many others. There are a bunch of supervised learning problems, categorization, function learning, and stuff like this. We have a lot of Markov decision processes, reinforcement learning problems. There's some probabilistic reasoning, a lot of decision making, some working memory, long-term memory, and a few other ones. Just to give a short feeling of how these prompts that we created in this process look like, it's very similar to what I've shown in the example from the PNAS paper, but I think it's good to remind us again. So essentially, the idea was each prompt should correspond to a single session from one participant doing the experiment and contain all the information that the participant has seen or produced in that experiment. It starts again with short introduction. So here we see an example from the Horizon task again. We tried to mirror the instructions as closely as possible as they were stated in the original experiment whenever that information was available. But in some cases, we had to make a few changes because the format of presentation is not the same. People get this in visual format sometimes, and here we have to translate all of this in text. But we tried to stay as close as possible to the description that people get in the experiment. And then it contains essentially all the information of all the trials in the experiment. You see for some of these tokens here, they are marked in yellow and in orange, and in special tokens. And we mark these tokens specifically because these correspond to human choices in the experiment. And we only want to fine-tune a large language model on these specific choices. We don't want the model to produce the entire description of the experiment. We only wanted its choice behavior to become more human-like. And this is what we use these markers for, so that we can identify these tokens on which we specifically want to fine-tune on. Here's a second example. This is from a similarity judgment task. So here in this task, you're presented with triplets of objects, which will be assigned to different keys. And in each trial, you have to essentially pick the odd one out object, the one that is most dissimilar to the other objects. So you have, for example, Z is prune, M is nail polish, and Y is cat. And then people do a certain choice. In this case here, the participant pressed I, indicating that participant thinks that this cat is the odd one out object in this case. And then continues for the entire choice history of the participant. So we take this huge data set that we have created here and we want to fine-tune a large language model on it. For this, I want to talk about a few technical details, but I don't want to dive too deep into it, but happy to chat more about this later on if people are more interested. The base model that we're using for this is called Mistral 7 billion. It's a state-of-the-art large language model with 7 billion parameters. So probably a bit on the smaller to medium size. We chose this model specifically because it's so large that we can fit training and fine-tuning on a single GPU, which makes it easier for us to train these models, but also for people, if they want to use these models that we're creating here later on, they can simply run them on a standard consumer computer without needing access to a big cluster. And the second point is that this model actually has quite a long context range, so you can fit quite a lot of words into it. And that was important to us because when you transcribe some of these experiments into a text-based format, they can become quite long sometimes. When you have to describe everything that happened to a participant, suddenly you have filled like pages and pages of text when you do that. So we take this model, and this is a standard causal transformer model, which consists of these transformer blocks. Series of multi-head attention, layer normalization, feed-forward networks, bunch of residual blocks, and so on. And one option that you could do is you say you fine-tune each of these transformer blocks directly on the data set that we have generated. Now that has two disadvantages. First, this model has a lot of parameters, 7 billion, and while the data set that we have generated is large, it's probably not large enough to avoid any kind of overfitting in this process. So we have, if you recall, 15 million human choices, and when we want to fit a model with 7 billion parameters to that, probably we are in big overfitting trouble. And second, if we would fine-tune the original model directly, we would lose a lot of information that is present in these models. But that is precisely the information that we want to maintain to give these models here like a lot of background knowledge about the world that they can then use to generalize to vastly different settings. So instead, what we are doing is we are adding these so-called adapters to each of the feed-forward linear layers in this model. So these adapters add a few trainable parameters for each layer in the model. The particular adapter that we're using is called a low-range adapter, which has one trainable weight matrix to each linear layer in these models. And this weight matrix can be expressed using a low-rank factorization. So when you do this and do this for each of the models, you end up at probably close to around 1 million parameters that you're training, which is much less than the total number of parameters that the model has. So we take this model, take our data set, and then fine-tune for 5 epochs on this data set using a method called QLoRa, which essentially does exactly what I said before, just using a quantized version to save a bunch of computational resources. And this results in a model that we call Centaur 2, essentially because an extension to what we did in the turning large language models into cognitive models paper. So we then wanted to take that model and see how well does it predict human behavior. Really, did the kind of fine-tuning process that we did here actually work? For this, we tested the model on all of the experiments that were part of our training data set, but we tested it on new participants that were not part of the training data. So this is perhaps the weakest test of out-of-distribution generalization that you can do. Test here that you will see is same task as in the training data, but new human subjects. Here you see how well these models predict human behavior. On the x-axis, you see a pseudo R-squared value, where a value of 1 corresponds to being perfectly able to predict human behavior. Value of 0 corresponds to prediction at chance level. And then you see 2 colors here. The purple color is the performance or the goodness of fit of the fine-tuned model, the Centaur 2 model. And the pink one is a base model without any fine-tuning, so that is the Mistral 7 billion model. Few observations here. First of all, both of these models are actually to predict human behavior fairly well. They are pretty much above chance level in all of these tasks, no matter if the model was fine-tuned or not. Then second, there's also a lot of variance in how well human behavior can be predicted. Predictions in some of these tasks is fairly easy. For example, in the serial reaction time task or in the BART, prediction is fairly easy. Humans are not so noisy. But then there are other tasks, like a decision from description setting or categorization tasks, which are typically much harder to predict because people are much noisier there. Now, most importantly, however, here in this plot, we see that Centaur purple is generally much better than the original base model that was before any fine-tuning. We see performance increase of the pseudo R-squared value by around a factor of 2, I think, on average, if you look at all of these tasks. So really showing that fine-tuning these models on behavioral data can make them much better at human predictions, even for participants that were not part of the training data. Now, this is in terms of just showing fine-tuning helps in terms of relative performance, but we are also, of course, interested in absolute performance. For this, we took Centaur 2 and compared it against a bunch of traditional domain-specific cognitive models that have been handcrafted for these specific domains. So this is still work in progress. We have not done this for all of the tasks that you're seeing here, but just for a subset of those. That's why there are so many missing bars here. But in general, what you see for the tasks that we looked at so far, we see that Centaur is better at predicting human choices than pretty much than the traditional cognitive models in pretty much all of the cases. There are a few exceptions here, maybe this probabilistic instrumental learning task we are trying to understand right now. I think it could have to do with that this data set is actually quite small that we're using for this, but I think one has to look closer once we have all the results from all the tasks. So really this shows that the model is actually quite good at predicting human behavior on an absolute level as well, and even outperforms traditional cognitive model in terms of predicting human behavior. Then we wondered, okay, how well does Centaur 2 actually generalize to completely new tasks? Because that is why we went into this whole trouble of fine-tuning a large language model that has all of this kind of background knowledge with the hope that we can actually get a model that generalizes quite well to completely new settings. For this, we did a bunch of tests, 3 so far that I will present. The first thing that we looked at was we tried to see, is the model robust to a change in cover story? For this, we looked at a 2-step task, which is, as I said before already, a task to disentangle model-based from model-free reinforcement learning. In this task, the participant starts an initial state here, this green state, where it can choose between 2 different options. One of these options predominantly leads to the pink state, but sometimes it also leads to the blue state. And the other option predominantly leads to the blue state, but sometimes can also lead to the pink state. And then in each of these second states, you encounter 2 objects again. You have to select one of these objects and you get rewards based on whatever object you select. Now, typically when people run this kind of experiments, it's really one of the most canonical experiments in cognitive neuroscience literature. They use a cover story that involves traveling on spaceships to foreign planets in order to find treasures. And this kind of cover story is also part of our training data. But we wanted to see, can this model generalize robustly to a change in cover story? And for this, we looked at a study that was conducted in this paper here by Da Silva and Harrell, where they proposed a different cover story for this task, where you have this magical carpet on which you can fly to either the pink or the blue mountains, where you can potentially encounter genies that give you some coins. And the authors on this paper, they argued that this change of cover story actually encourages model-based reinforcement learning, makes people more model-based. So we want this, importantly, this cover story is not part of our training data. This cover story is part of our training data. So we wanted to see, can we predict human choices in this experiment with this new cover story? Plot here shows the result of this, again measured in pseudo R² values, so higher means better. And we see Centaur 2 is again much better at predicting human choices than the base model before any fine-tuning. And we also see that it again, even in this out-of-distribution test, outperforms a domain-specific cognitive model. For this, we have taken a standard reinforcement learning model, fitted it on data from this behavioral paradigm with this cover story, and then tried to see how well does the model with these parameters predict human choices in this new experiment. So here really indicating this model that we have generated is at least to some extent robust to changes in cover story, can deal quite well with that. Then we wanted to see, can Centaur 2 also generalize robustly in the face of minor modifications to the task structure? So in our training data set, we have a lot of 2-armed bandit problems, like the horizon task that I talked about before. But we don't have any 3-armed bandit problems where you have a third choice option suddenly. So we wanted to see, can a model that is only trained on 2-armed bandit problems also generalize robustly of predicting human behavior, which do the 3-armed version of the horizon task, which is taken from this paper here by Dubois et Hauser. Again, here's the plot with the performance. We see Centaur 2 again predicts human behavior quite well in this task actually, reaches a pseudo R² value of 0.6. We see this, again, relative benefit of fine-tuning when comparing to the base model. And perhaps what was most interesting to me was that a traditional domain-specific model, cognitive model, completely fails to predict human behavior in this paradigm. And that is because this model is, again, a standard reinforcement learning model, for which we fitted the parameters to this version of the task. And then we tried to see if we only add a third choice option in the task, can the model with the fitted parameters on the 2-armed version also predict behavior on the 3-armed version? And we see the model completely breaks through this minor modification versus Centaur 2 is fairly robust to it. And lastly, we wanted to see, can we exchange a complete component of the task? For this, we looked at a study from Janssen and al. Studying the Dunning-Kruger effect, which is a fact that people, especially low performers, tend to overestimate their performance. And in this paper here, they had 2 versions of the task. They had this version here, where first people do a self-assessment, then they do a grammar judgment, and then they do another self-assessment. And the self-assessment is always something like to answer, how good do you think you are at making grammar judgments? How good do you think others are at making grammar judgments, and so on. And this version is part of our training data, but the paper contains a second version where the grammar judgment task is exchanged with a logical reasoning task. and that is not part of our training data. So we wanted to see, can Centaur 2 also predict human behavior in this version of the task? Again, we look at performance, measured against pseudo R² values, and we see, again, Centaur 2 is quite well at predict, or quite robust to this change of the task, can still predict human behavior quite well. We again see a benefit of fine-tuning. And baseline model we don't have yet, so that is why this line is at 0. So, but I would assume that it's also somewhat similar picture to what we have seen before, can predict a bit, or it completely breaks. That we have to see once we have implemented the model. Cool. So up to now, I have basically shown Centaur 2 can predict human behavior quite well. It generalizes, at least to some extent, to new cover stories, to changes in tasks, to exchanging structural components. One thing that we were also interested in is what happens to the internal representations of the model. How does the model represent information internally? Do these internal representations become more human-like, even though you only fine-tune on human behavior, but never on any human neural activity? So for this, we looked at a study from Tukuta et al., where they essentially put human subjects in a brain scanner, measured fMRI recordings, of these subjects reading a bunch of different sentences. So these sentences were always simple 6-word sentences, something like "were all the vampire stories true?" And then they recorded fMRI responses of participants in the setting, and at the same time they extracted internal representations of a large language model. In this case, this was GPT-2 XL. And then they tried to see, can you predict the fMRI measurements based on the internal representations of the model using a linear encoding model? I should say this kind of setting that we are investigating here is really far away from the training data that we have used to train Centaur 2, because there we use these kind of cognitive science, cognitive psychology experiments, whereas here it's really like people reading these simple 6-word sentences. So I think this kind of setting here is really a true test of generalization. Here are results for this when we try to see, can we predict human fMRI recordings based on activations of Centaur 2 reading the same sentences. Plot here shows R² values, so higher means better decodability for different layers in the model. In purple, we see how well Centaur 2 is able to predict human neural activity, and in pink, we see how well the base model, Mistral 7 billion, without any fine-tuning, is able to do the same. And we see there's a constant increase in R² value from Centaur 2 compared to the model without any fine-tuning, indicating really there is a robust effect of model processes information in a much more human-like, or in a more human-like way after fine-tuning. And I think that is really surprising to me, because these stimuli here are so far removed away from the training data, and we didn't even train these models to mimic human neural activity. It's just we mimic them to train human behavior. There are 2 more additional lines here. There's the gray dotted line, which is the number reported in the original paper. This is a bit lower than what we report here, essentially because in the paper they used a quite old model, GPT-2, and the model that we have here is more powerful than GPT-2. And then we have also noise ceiling. This is the black dotted line here. And we see actually we are not too far away from noise ceiling anymore, almost predicting human neural activity at the noise ceiling level. I think that's also quite surprising to me. So to wrap up this part, I've talked about Centaur 2, which is perhaps the first foundation of human cognition. It's obtained by taking a large language model and fine-tuning it on this large behavioral data set that we have generated. Centaur 2 is able to predict choices or choice behavior of holdout participants quite well, and it even generalizes to novel experiments where we modified cover stories, we made smaller structural modification to the task, or when we exchanged an entire task component. And then finally, we have also found that the internal activations of these models become more aligned with human neural activity. And to me, this is kind of a proof of concept that you can now discover these unified models of cognition that I talked about in the beginning in a data-driven manner. Now, there are many direct applications for such a model. For example, you can use it for prototyping your behavioral experiments. Earlier this morning, I had a conversation of how you may be able to use them for running power analysis. You can also use them for optimal experimental design, kind of ask these models, okay, how do I have to design my study to observe a a strong or weak or no effect. You can even use them for automated discovery of cognitive theories, where you simulate behavior and then use this toolbox of automated cognitive science to figure out how they solve these tasks, and that you can use to generate predictions of how people might solve these tasks, and then you can test these predictions in subsequent experiments. Or you can use them for training human-in-the-loop system, where you have an artificial agent that somehow has to interact with people, and you want to train the system that it can do so in a meaningful way. And that is typically challenging because you have to somehow place the human in the system and wait for human interactions, which is quite slow. But with a model like Centaur 2, you could just plug in that model instead. Now, I think these are all cool applications, but ultimately what I'm interested in is using these kind of models and tools that I presented to learn something about human behavior. Now, I think with the stuff that I presented, we are not quite there yet, but I think there are quite a few cool avenues that I'm really excited about to pursue in this direction. And perhaps the one that I'm most excited about is that you can take this data set, this large-scale data set that we have created here, and not only fine-tune language models, but instead train neural network models from scratch on this data set. And that really would allow you to investigate the neural architecture of human cognition at a scale which we could have not done before. For example, you can ask questions like, is human information processing better described by models like transformer models? Is it better described by recurrent models? Do you need ideas to incorporate ideas from neuroscience, like predictive coding, or do you need to rely on ideas from computer science, like backpropagation? And I think in this process, once we take these models and fit them to the large data set, we will discover new architectures even that are even better descriptors of human behavior than the ones that we currently have. And my hope is also that some of these architectures that we discover in this process can form future machine learning systems. So, and I think once we are at this stage, once we fit these models from scratch, we can really move a big step closer towards answering the question of how do people manage to accomplish all of these amazing things that I talked about in the beginning. How is it possible that you can pretty much throw whatever task at people and get some meaningful responses back? And with that, I'm for more slide actually. Attention. So basically, I think if some of the stuff that I talked about, you find it interesting and you think I want to apply language models to my own research, recently co-authored this paper, a tutorial paper on using open source large language models for behavioral science, which I think is a really great resource for trying to understand how these models work. The GitHub code here contains many notebooks with really good examples for many use cases, generating text, extracting probabilities, extracting internal representations, and so on. And perhaps the most interesting thing is that you actually don't need a lot of computational resources to play around with these models. All the stuff that we have as part of the tutorial can be run on a single Google Colab notebook without even having access to any kind of cluster. And with that, I'd like to thank you for your attention. Thanks my lab and all the collaborators for their help in these projects. And thanks for inviting me.
If I'm allowed, first of all, thanks for the great presentation. I mean, it was filled with great technical debates and insights. So thanks a lot for that. I'm not a psychologist as a background, so you will forgive me do some, let's say, remarks I will try to do in that respect. But I do see a couple of elements in the room which I would like to discuss with you.
Sure.
Especially in the passage between slide 32 and slide 33. So basically, in the claim that by the means of doing what you're planning to do, you will achieve a better understanding of the overall, let's say, cognition processes of the human mind. So in this respect, I'm puzzled by a couple of things which I would like to share. First of all, you spoke a lot of times about human behavior, which I do understand incorporates human biases.
Definitely, yeah.
So while you mimic human behavior, you are also mimicking both biases and incorporating those into the model.
Definitely, yeah.
So maybe I have a different kind of, let's say, goal in mind, which is more to replicate and maybe overcome human intelligence, which would actually mean to overcome
the maximum that people can achieve, yeah.
And it seems to me, but also to the help of Meta AI data scientists, that it's going to be kind of impossible to overcome human intelligence by means of large language models because of the limitations which are intrinsic to their structure, especially when it comes to the internal representations you were showing before. So, in spite of having a progress in that respect, I do ask, what's your view in respect to the structural needs that those representations might have, and how do you comment on the claim that maybe general world models could be more suitable for that task?
Yeah.
That's one thing, sorry. Second one is...
can I answer to this already, because my memory is not that good? So I think two things in that regard. One is, I think my goal here is definitely to try to understand human behavior and not create like a system that exceeds human intelligence. But I think that is an interesting question in itself. And I think regarding the statement whether we can do the second thing using something that is based on large language models, I think that is pretty much an open question. And I think that is where it depends a lot on where you draw the line of what is a large language model and what not. Because like certainly things like GPT-4, they are not just large language models anymore, but there's a lot of background stuff going on, right? There's a web search engine, there's a code interpreter, they are trained on a bunch of other things. So when does a model not become a language model anymore, I think is crucial.
Interesting enough, they claim GPT-4 to become a Turing test.
Yeah.
So, which leads me to the second question. Because you evidently mind a paradigm for what it is, good metrics for understanding whether you achieve your goal or not, which to me is a daunting task in itself. So to have a test or a battery of tests which apply to a machine can give us the answer as to being it human-like or not. So I would like maybe you to elaborate a little bit more on what you have in mind when you say this is more human-like or less human-like. What do you exactly mean by that?
So in this case here, we always mean that the system is able to predict human choices in these experiments, right? And then I guess the interesting question is how does that generalize to real-world situations as well? And I think that is a whole research agenda to figure that out on its own again. Thanks a lot.
The human behavior is well-known fact in research, in the sense that we have a positive mindset. Multiple cognitive abilities are positively correlated.
Yeah.
Is there something similar also in this foundation model? Are you planning to study the G factor of ChatGPT?
Yeah, that could be an interesting test for out-of-distribution generalization, I think, actually. You could basically, because stuff like that is not part of our training data here, right? But you could imagine that after training on a lot of these experiments, that you can do something like that, some correlation analysis as well, and see whether you find that. Could be quite interesting.
Thank you. I was wondering where you push yourself in this comparison between your model and the human mind.
Mm-hmm.
So on one side, you might say that you provided an LLM with all the tasks available, and LLM, of course, is a powerful regularity extractor, and it's more than expected that it will perform very well in predicting the human performance on those tasks. You did some attempts in seeing how much it generalizes, but we are not too far away from where we started, I would say, from this respect. So I was wondering whether your claim or your goal is to have go in the domain in which you say something along the lines that building these machines actually is a possible window in understanding how actually the human mind gets to do what it does. Yeah. So just to understand whether you're just planning to do something that perfectly mimics. So as it perfectly mimics a human, so it would be a fantastic tool, of course. Because so when
because there are not enough people.
There are not enough people. Also, it's very interesting to predict what would happen to a bunch of humans when they are put in some different context that you never tried before. Or actually, you think that looking inside and how this newly designed LLM works actually gives us a window in how what you would see here inside. And I mean, the last experiment that goes in that direction. So I was wondering.
I think the second thing is definitely the stuff that is closer to my interest and what I want to achieve in the medium to long run. But I think before we can get there, I think there are like a few in between steps to achieve. Kind of that is why I also said this is a proof of concept, essentially, that you can even discover human-like models in a domain general setting in a data-driven way. But I think ultimately I want to use these tools to figure out, I think this goes in this direction, but you could also think what you said, studying how the fine-tuned model processes information internally. Are there specific components that do this stuff? And then you could use that to generate new predictions about human cognition that you could then go out and test. And I think these two directions, I think is what interests me the most.
Thanks, really interesting. I think I will go on the line what Carlo asked. So let's say you want not to replicate the average man, but you want to specialize it for different universities, like engineers, like psychologists. How do you do that?
That is definitely the plan moving forward. So I think one very obvious way is to, when you have this information available for human subjects, just add it to the prompt. You could say, you are a 34-year-old researcher working in cognitive science from Munich, Germany, whatever, right? And there are a lot of studies which look at these kind of individual differences, computational psychiatry studies, developmental studies, and definitely the plan is to extend that data set much more in this individual difference directions in the future.
You have much less data.
You have much less data, but hopefully you have a lot of regularizers with having all the other data sets on top and the background knowledge of these models.
And that's more or less the second question. So you have a lot of comparison between the fine-tuning and Mistra, no? And usually Mistra is not so bad. Do you think there is a lot of data in the training set that is can actually replicate?
I don't think so. I mean, it's always hard to say. Probably at some point we will have to do an analysis that's showing that it's not the case to really convince the reader. But I mean, what's definitely in the training data set is temporal sequences where you have to predict complicated stuff, and that might be able to transfer to these situations.
Yeah, because in many cases, like if you rename everything in a task, sometimes
I think what actually happens internally over the complete session of an experiment, the model can pick up a lot of pattern on how a particular participant does in this task. And I think that might be very important to analyze. How does the number of previous observed examples in this prompt relate to predictability, how well the model is able to predict behavior?
Last question, how do you do the prediction of the response time, the serial reaction time?
So basically, I mean, it's a bit lame. In what is called a serial reaction time here, people have to press a button after they see another button, and we just look at the choice behavior, not the reaction times.
Okay.
And so that is why it's a bit of a lame task, kind of. I think
you don't predict the reaction.
We don't. I mean, you could, but we don't. The information in this task is actually part of the prompt. So it says something like you saw a button or you saw key blah, 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 you press button, blah, 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 in that and that time frame. So potentially you could predict reaction time. We don't yet, but I think that is also an interesting direction. Do you want to add reaction time to be able to predict it in these models whenever you have that information available?
This would be like numerical value.
Yeah, I mean,
Like
once you embed this reaction time into architecture, I think that's where it gets complicated, but you could predict a numerical number.
I think that one very interesting thing of this whole endeavor is when you show that training on behavioral data using the brain data, because it is taking two different things and you're not like training on behavior and that's behavior. I was wondering whether you had in mind of doing the opposite thing, like, and you have any reason on that, like devising some kind of loss function that depends on the behavioral data to brain data and see how.
Yes. So if you fine-tune a model on brain data, do you also get more choice behavior? It's not something I've thought about before, but it could be quite interesting to do. Yeah, that would give you very strong insights, perhaps, into like the actual processes and so on that could go on.
And do you expect to find like this things?
Yeah, hard to say. I mean, creating this data set for the behavioral data is also like already like a huge challenge because in psychology the data is all over the place. Everybody has their own format, and just cleaning it up and so on. And that would be even more challenging when you work with brain data. So that's why I've never thought about it. But if one would take the effort, I think it could be quite interesting.
So thank you for your talk. It's two questions in one. So I guess the behavioral data sets was taken from different studies. So you can say, I mean, very different samples.
All open source, publicly available data. Yeah.
How are you planning also to collect a big, data from a big sample? Because I would guess that despite the very different tasks, you have some shared variance.
So where people do multiple tasks as well. We have not planned that. I mean, there are some studies that do this that could be potentially used for this. Yeah, but we haven't planned on it. So some of the studies that we have in here are actually part of larger meta studies. So that could be directly used even for that already.
And related to this, I was wondering whether the fine-tuning step was a sort of parallel fine-tuning or rather incremental separation. So rather than looking at the performance once you fine-tune all the tasks, you look at the performance of the model once you fine-tune on.
So you do like a sequence of, no, we basically shuffle everything, randomized.
There may be some hierarchy.
That is true, but then I think one difficulty that you have when training neural networks with gradient descent, they kind of expect your data to be IID distributed, and then once you bring some structure in, they often fail. So I think it would be very interesting to investigate. I think just the toolkit that we have currently available is not the perfect fit for this.
Connect to this question. Two questions, one as yours. So is this the performance in predicting human behavior is already superhuman? So it does better than.
I would assume people are pretty. I mean, what is a human that predicts human behavior? Isn't that just a human doing the task?
I'm just curious. So you observe that, so it's already way beyond what we can.
I mean, that would be
a bunch of people can do.
That is hard to say. I mean, I think what you're describing would be how, if you say the human predicting the task is a human doing the task, then superhuman would mean above noise ceiling. And so
before you can form, if you see a task and you try a few trials, you can form your expectation how an average human would be.
I think if you actively ask humans to predict what, so for example, I would give you this prompt here and hide this and ask what would that human predict. I think people would be quite bad at it.
Yeah. I mean, it's like metacognition. You know? So
Yeah.
It's a task that we often need to do because we need to estimate how good are people around us in solving problems that we have.
Yeah, no, it's an interesting question. Like, how good are people when you ask people to predict? Yeah.
And the second one that is connected to that, is the machine aware of human variability? So now it predicts the average.
Yeah.
But is it aware that
Not-
some tasks are more, some tasks
Not-
has more or less variability?
Not explicitly. The only way how it can find this variability is by extracting patterns in the sequence that you have seen up to a certain point. Right. So, for example, if you have a risky choice task and you have 100 trials where a human is doing perfectly rational decisions, the model, I think, would predict onwards, okay, this particular human will make perfectly rational decisions for the next 100 trials.
Question. The participants in the studies that you have considered, they are the typical psychology student or third years.
Yes.
So what I was wondering is, maybe with your fine-tuning, you are making the model closer to expert at doing experiments.
Yeah.
And maybe the not fine-tuning model is closer to the natural person.
Could be. I mean, definitely you bring, because I think, you know, all psychology experiments are biased towards certain groups for sure. So I think something like that you will overfit to that particular group will certainly happen. We have some experiments in the data set, which are like these large cross-cultural studies as well. So that prevent that maybe a bit. But I mean, this is maybe like 5% of the training data that is in this format. But I think it would be important also for, like, when extending this data set, to think very, very strongly about how to avoid that potentially.
Another question? Marcel will be here for the next few hours, so we can exploit him if we want to. Thank you.
I have only a train to catch tomorrow at 2, so.
Perfect.
Right, thanks.